Hello and welcome to this clip going through the question 2 from the Chemistry Olympiad 2013 paper. This was taken the year after Bradley Wiggins won the Olympic gold in cycling, and it covers a little bit of redox titrations to do with the percentage mass of copper in his bronze medal, or a bronze medal, and also a bit of PV equals nRT that is to do with the pressure of the air in bike tyres. So two different places in the specification, but both really useful, and hopefully it'll be a useful sort of challenge to push you forward a little bit as you approach your final exam. So looking through part A, you actually have quite a lot of data and information that you need to sort of separate out. So we now need to think about what the question means. So just remembering that bronze contains copper metal, which in itself reacts with nitric acid in a redox reaction. And what we need to do is start with what we can work out the moles for. And this is called the data moles equation moles answer method. So if we lay it out like that and then just expand a little bit on what each section means. So looking at the data initially, that is essentially what data you already know from the question, which allows you to work out a certain mole value for one of the reactants or products, which then means you can work out the moles of everything else from the balanced equation, therefore identifying the moles of what it is you're trying to work out, and finally converting that moles into the answer that the question is directing you to try and find. Okay, so if we insert the values in that we've got, we can see that the volume of thiosulfate that's used in the titer is 12.20 centimeters cubed, and the concentration is 0.100 moles per decimeter cubed. So that means we can work out the moles of thiosulfate that was used. So doing N equals C times V, we get 1.22 times 10 to the minus 3 moles. So from the equation, the number of moles of copper equals the number of moles of thiosulfate. So that means the number of moles of copper metal in the 0.800 grams of bronze that's taken from the medal would also have 1.22 times 10 to the minus 3. So we can work out the mass of copper by taking the number of moles we have times its relative atomic mass. I'm using 63.55 from the Chemistry Olympiad periodic table that you get with this paper. So now what you can do is work out the percentage by mass by taking the mass of pure copper that this titration tells you you've got, which is 0.775 grams, dividing it by the mass of the sample of bronze, which is 0.800 grams, and multiplying it by 100. So that comes out as 96.875%. So this question is looking at working out the volume and then therefore the density and therefore the mass of a silver medal. So it assumes that you already know that the volume of a cylinder, which is basically what a medal is, it's going to be a slice out of a cylinder, isn't it? It's going to be V equals pi r h. And I think the h is actually the r is actually squared, like that. Okay, so we have a silver medal that has a diameter of 85 millimeters and it's 7 millimeters thick. So putting the numbers in, you end up with 39.726665 centimeters cubed as the volume of your silver medal. So the next part of this question is requiring you to think about the relationship between mass and volume, in other words the density. So to get the density of the medal, you have to remember that it's got a certain percentage of copper and a certain percentage of silver. So if we take the values that were given for the densities of each of those metals, multiply each one with the equivalent percentage by mass and then add it all up, that should give us the density of the medal. So expressing the percentages as decimals, you can multiply them that way, which gives us 10.37525 grams per centimetre cubed. So they want the mass of the medal. So rearranging the density equation to make mass the subject, that gives you density times volume. So putting in the numbers that we've worked out, keeping to the calculator numbers, obviously, we've got 412.1740551 grams as the mass of your medal. So part C takes things a bit further. They start talking about gold medals now. Now, a gold, quote-unquote, medal in the Olympics is actually a mixture of gold, silver and copper. So each of those metals is going to behave in a slightly different way if it's reacted with HNO3 and then HCl. So you've got to think carefully about what's going on here. You may need to do a data moles equation moles answer again. So it finally tells you at the end that the precipitate formed when hydrochloric acid is added to the resulting mixture is 6.144 grams. So if you think about what's going on, first of all you take your medal, or the sample of your medal, and you put it into nitric acid, and what's going to happen in the nitric acid is the silver will form silver nitrate, but in solution. So that stays in solution, and then your HCl is added, and the silver nitrate in solution will react with the chloride ions to make AgCl. So the AgCl is your precipitate they're talking about. So you've got 6.144 grams of AgCl. So we end up with 0.042869141 moles of silver chloride precipitate. So that gives us an equal number of moles of solid silver, because AgCl to Ag is a 1:1 mole ratio, as you can see from the ionic equation. So from this, what they want us to do is the percentage by mass of gold, silver and copper. So to work out the mass of copper, first of all, you need to take the total mass of your medal or your sample, and from that take the mass of the silver and the mass of the gold. Now it said an undissolved residue is separated by filtration, wash dried and weighed, and its mass was 0.067. You can assume that the gold is that, because gold is the most unreactive out of the metals, which leaves us the difference, which will be the silver. Now we can work out the mass of the silver from the number of moles. So working all that out gives us 0.067 grams for our gold, 4.6242926 grams for our silver, and 0.30870974 grams for our copper. So if we take each mass and divide it by 5, which is the total mass of the sample from the medal, multiply that by 100, you get 3 percentages that hopefully add up to 100, or very, very close to it. Okay, so the next part of the question I have to put a new screen on. So we just go to the bottom. It says the GB cyclists have individually designed bikes which have to cope with the demands placed on them whilst being as light as possible. So one way a light bike could be achieved is by altering the gas used to inflate the bike tyres. So we're now switching our focus onto the gases that are used to inflate the tyres. So this part of the question looks at the ideal gas equation, so it's shifting from one part of the A-level chemistry specification to another. So it explains PV equals nRT, which if you're doing this as a second year, you'll have come across this in your first year. And it's got some data for you to use. It also includes R as the gas constant as 8.31, not 8.314 as you may have in your data sheet. It also tells you how to calculate the volume of a torus, in other words like a donut shape, and it gives you a diagram to help you think your way through this as well. So if we go to part D, so in this one you need to have everything in meters. So you take 66 centimeters and 23 millimeters and convert them across to meters. So using the information we're given about how to work out the volume of the torus, we have to think about what R is. R is not necessarily just radius. So R is the distance from the center of the torus to the center of the tire tube. So that means you have to halve the wheel diameter and halve the tire diameter. So that gives you 0.33 minus 0.0115, which is 0.3185 meters. So I've just labelled it there. So the centre of the torus to the centre of the tire tube, that's your R. So that's 0.3185 meters. So that gives us 8.316631799 times 10 to the minus 4 meters cubed. So moving on to part E, the first part asks you to calculate the number of moles of gas in the tire at 25 degrees C. So if we put the numbers in, we can quite easily work it out. So I nearly made a mistake there. In my pressure, I forgot that they'd said that 6895 pascals is 1 pound per square inch, psi. So we have a pressure of 120 psi, so we need to multiply 6895 pascals times 120. So putting the numbers in one more time. So that gives us 0.2778725859 moles. So the next question asks us to calculate the total mass of air in both tyres on a bike. So we need to take into account the fact that there's 80% nitrogen and 20% oxygen. So therefore we also need to take into account the grams per mole of a nitrogen molecule and the grams per mole for oxygen molecules. So take into account the percentage by mass times the molar mass in each case, and you need to multiply all of that. That's for one tyre. I've just realised it shouldn't be 16 in the bracket for oxygen, it should be 32. That gives you 28.816, and that must be now multiplied by the number of moles in one tyre. Giving you that value in grams, but they want it for two tyres, so that needs to be doubled. So that gives you 16.0143527 grams for both tyres. So the next part asks you to calculate the reduction in mass if both tyres were inflated with helium instead of air. So doing the same calculation for helium, you get the mass of helium in two tyres being 2.274647923 grams. So the difference between the original that we had and that is what we need to work out, which gives us 13.78970495 grams, which is a massive reduction, isn't it? Okay, so final bit is asking us to think about what would happen if we had sulfur hexafluoride as the gas in the tyre instead of helium. So obviously this is going to be a lot greater in mass. So adding up all of the individual grams per mole for each element, you need to work out the total for SF6 is 146.06 grams per mole. So we're doing the same calculations before, but incorporating 146.06, we get 81.172139979 grams as the mass this time. So they want the mass increase, so you have to take your 16.02 grams, which is what has the normal nitrogen-oxygen mix that they normally use, away from this. So inserting the exact calculator values, we get 65.1577869 grams as our increase. Okay, so that takes us to the end of this question. Hopefully it was quite useful, both in terms of its review of redox titrations, but also a look at PV equals nRT in the context of something that's been in the news recently as well. So until next time, thanks for listening and see you soon.